Welcome, Wildcats. Today we're going to be introducing section 1.2 out of your textbook. In 1.2, we're going to be talking about all of the different families of graphs that we'll be talking about throughout the whole year. Specifically for 1.2's beginning, we're going to be looking at linear, absolute value, and rational functions. And we're just going to be talking about how each of those graphs look and a few of the characteristics. So for each of the graphs that we're going to look at today, we're going to identify a few specific traits. We're going to identify their domain and range, what that looks like, their x and y intercept. So your x-intercept is where you cross the horizontal axis, the x-axis, and your y-intercept where it crosses the y-axis. We're also going to talk about the maximum number of roots that a graph can have. Your roots is the same thing as your zeros, so it's whenever the f of x yields a zero result. We'll talk about that here in a minute. We're also going to look at the end behaviors of all of the different parent functions, and then we're going to talk about whether or not these graphs are continuous or if they're discontinuous. So let's start with our linear function. Linear functions are always a straight line, but it doesn't matter what direction that line goes. Any direction, it is linear. The graph that I have on the screen for you is the parent linear function, which is f of x equals x, or y equals x. The domain for all linear functions, not just the parent function, is all real numbers, negative infinity to positive infinity, both for your domain and your range. Your x and y intercepts are unique to each linear function though. The parent function we can see in this case, it crosses both the x and the y-axis right here at the origin. So because it crosses the x-axis at 0, 0, that's your x-intercept. And because it crosses the y-axis at 0, 0, that's your y-intercept. Now if you think about it, because we have a straight line here, how many times can this graph cross the x-axis? That's going to give us our maximum number of roots. Yeah, it can only cross one time because it's a straight line. It can't double back on itself. We can see for this case that our end behavior of this graph, as x goes to our left, or as f approaches negative infinity, our y approaches negative infinity as well. Our f of x approaches negative infinity. And then as x goes to the right, as x approaches infinity, f of x approaches positive infinity. Continuous and discontinuous is something that we haven't talked about yet, but the easy way to think about it is if I can draw the graph without lifting my pencil, then that function is continuous. So think about a straight line. Any straight line I draw, I can draw it without picking up my pencil. So because of that, all linear functions are continuous. Next graph that we're going to look at is our absolute value function. Essentially, absolute value, if you have a negative number inside an absolute value sign, you just get rid of the negative. If you have a positive number inside the absolute value sign, you do nothing. So what that means is we take our linear graph, and instead of having it on the negative side for y, it gets reflected for half of it, and it becomes this V looking guy. So our parent function is f of x equals the absolute value of x. Our domain and range is going to be a little different. We can see here that our domain, our x, still goes from negative infinity to infinity, but we have a minimum for our y. How low does it go? It stops right here, which is at 0. But does it include 0? It does. So we have our bracket, and it goes all the way up to infinity. So our domain is negative infinity to positive infinity. but our range is only 0 to infinity. Please note that bracket, it does include 0. That's not true for all absolute value functions. This can shift up, down, left, right, so our range can change, but our domain for absolute values is always going to be all real numbers. The x and y intercept again can change depending upon the exact function, but for the parent function, it's again at the origin, 0, 0. That's both for your x-intercept and your y-intercept. But look, if you look, we no longer have a straight line. We have a straight line that reflects on itself. So how many times could this cross the x-axis? Well, we see that in this case it does only cross once. But the exact same kind of function could cross twice if it were drawn in a different location. So our maximum number of zeros is 2. The end behavior is going to depend on the exact function that you have, but for this specific one, for the parent function, we can see that it goes as x gets smaller, y gets bigger. So as x approaches negative infinity, y approaches infinity, and as x approaches infinity, it's still going up. So once again, y approaches infinity, or f of x approaches infinity. Just like the previous graph, this one, we can draw the entire thing without ever lifting our pencil. So that means our graph is continuous. Third and final function that we're going to look at today is the rational parent function. This is a graph that you probably have not seen before, but if you have, it may look very confusing. This is what the parent function itself looks like. So the reason we call it a rational function is because the equation of it has x in the denominator. It is a ratio. So the parent function itself is f of x equals 1 over x. Now, you have seen this specific graph before. It was a graph that I used in a previous video to describe asymptotes. And what we discovered in that video was that as we move further and further to the left, we get closer and closer to 0, but we never actually touch it. And the same is true to the right. We get closer and closer to infinity for the x value, and our y value gets closer and closer to 0 without ever actually touching it. So that means our domain goes from negative infinity to infinity, but you might remember that there's also this vertical asymptote here. As we go to a negative infinity, we get close to 0, and as we go to positive infinity on the other side, we get close to 0, but it never touches it. So because of that, we've got negative infinity to 0 and 0 to infinity for our domain. So it's the combination of those two. Remember, we're not including 0, so we have open parentheses. For our range, starting at negative infinity, and it does go up to infinity, but we have that same hole at 0 in the middle. So our range looks the exact same as our domain. Remember that your x and y intercepts are where they cross the x and y axis. But since this never touches 0 on the x-axis, we don't have an x-intercept. Same with our y-axis. So our x and y intercepts are none. If you look at the way the graph works, you're going to notice that no matter where you are, there's only one spot on the graph that associates itself to that y value. So because of that, we can never cross this x-axis more than once, meaning our number of maximum zeros, or our maximum number of roots, is 1. Now looking at our end behavior, remember we're just looking at left and right. So as x approaches negative infinity, f of x approaches 0. Looking at the other side, as x approaches positive infinity, f of x approaches, once again, 0. Now this graph, unlike the previous ones we've looked at, when I go to draw it, once I get to here, I have to pick up my pencil in order to come across to the other side. So because of that, all rational functions are by definition discontinuous. So with that, that should give you all the information that you need in order to do the first set of problems within your 1.2 homework assignment. Those will be linked in the description below.